An ICE table is a way of organizing given and calculated data. The three letters in the acronym stands for initial concentration, change in concentration, and equilibrium concentration. The best way to learn how to utilize an ICE table is to go through an example. An equilibrium was established after 0.1 moles of hydrogen gas and 0.1 moles of iodine gas were added to an empty 1 liter reaction vessel and heated to 700 Kelvin. The fact that an equilibrium was established after this happened indicates the fact that we are not yet at equilibrium for the 0.1 moles of hydrogen and iodine, and this is the indicator that we require an ICE table. Recall that the letters in the acronym of ICE represent initial concentration, change in concentration, and equilibrium concentration. Therefore, the only thing we can plug into the ICE table are concentration values. In this question, we were told we had 0.1 moles of hydrogen with 0.1 moles of iodine in a 1 liter reaction vessel. Therefore, we need to calculate the concentration before we set up our ICE table. Recall from Chemistry 2202 that concentration is equal to the number of moles divided by the volume, and the volume must be in liters. Even though we're only dividing by the number 1 here, and this is a very simplistic calculation to do in our head, remember that you must show the concentration calculation in your notes. Otherwise, I don't know if you knew you had to convert to concentration and it was a simplistic calculation, or if you forgot and you plugged in the moles. Once we've calculated the initial concentration of hydrogen and iodine, we can go ahead and we can set up our ICE table. We just calculated that the initial concentration of hydrogen and iodine was 0.1. So we'll put that in the initial line for both hydrogen and iodine. When we talk about initial, we're talking about at the very instant that the hydrogen and the iodine have been introduced to one another. At the very instant that hydrogen and iodine have been introduced to one another, not enough time has elapsed to create any products. So the initial concentration of the hydrogen iodide will be 0. This will be the case for any ICE table unless I tell you initial concentration of a product. Then we have to think about the change in the concentrations. Consider the fact that we have 2 reactants introduced to one another. We talked about it in a few lessons ago. If we have the 2 reactants and they are first introduced to one another, then it should make sense that these 2 reactants are going to go ahead and make products. Because of that, we're going to lose some of the reactant molecules and we're going to make some of the products. So, since we're losing reactants, we represent that with a negative sign, and since we're gaining products, we represent that with a positive sign. Well, how much are we losing and gaining? At this point, we don't know. Since we don't know how much of the reactant we're losing, we will represent that with the letter X and X. We also don't know how much of the product we're gaining, so we'll represent that by X as well. However, notice that comparatively using the mole ratio, we have twice as much hydrogen iodide than we do of either hydrogen or iodine. Since we have twice as much hydrogen iodide being formed for every 1 mole of hydrogen and iodine, we're going to represent this by plus 2x to show that we have twice as much gained as what we lost. Lastly, the equilibrium line is what happens after the initial and the change has happened. Therefore, the equilibrium line is the initial and change lines put together. So this will be 0.100 subtract x, 0.100 subtract x, and 2x. Once you've set up your ICE table, you then go back to the question for what I call the extra piece of information. And in this question, we were told that at equilibrium, the concentration of iodine was 0.0213. So the iodine at equilibrium is 0.0213 moles per liter. And according to us and our ICE table, the equilibrium concentration of iodine was 0.100 subtract x. This now becomes an algebraic expression where we need to rearrange to solve for x. And once you rearrange, you get x is equal to 0.0787. And I strongly encourage that you pause the video at this point, haul out your calculator, and make sure you get the same answer. Once you know the value of x, you can now plug in that value of x in the equilibrium line to get all of the equilibrium concentrations. That's essentially what we're looking for in this question. So HI at equilibrium, in our ice table we said that was 2 times x. We now know what x is, so we multiply the x by 2 to get 0.158. And since we're solving for concentration, we put in moles per liter or molar. H2 at equilibrium was 0.100 subtract our value of x. So we get an answer here of 0.0213 molar. Example number 4 says that an equilibrium was established in a 1 liter container when 0.120 moles of phosphorus pentachloride gas was decomposed. There's nothing in this question that states that the 0.210 moles is already at equilibrium, so this is how I know I need to set up an ice table. Additionally, recall from the last example that the only thing that we can plug into an ice table are concentrations. And in this example, again, we were told that we had 0.120 moles in a 1 liter container. So even though the math is simplistic, we still need to calculate it. Once you've shown the calculation for the concentration, you can go ahead and you can set up your ice table. We just calculated that the initial concentration of PCl5 is 0.120. That's our only reactant. As soon as the timer starts for the initial concentration and for the reaction to occur, we do not have had enough time elapsed to create any of the product, so that will be represented by 0. Again, we're going to lose reactant as it's converted over to both products. All of the coefficients in this equilibrium are 1, so all of our variables will only be 1. And then the equilibrium line is the first to put together. 0.120 subtract x, x, and x. Once you have your ice table set up, go back to the question for the extra piece of information. And here we were told that at equilibrium, the concentration of chlorine gas is 0.0540 molar. According to us and our ice table, the equilibrium concentration of chlorine was x, so we've now solved for x. Once you know what x is, you can then find the other equilibrium concentrations. PCl3 at equilibrium we said was x, so that's also 0.0540 molar. PCl5 at equilibrium was 0.120 subtract 0.0540 to give us 0.066 molar. In this question, we were also asked to calculate the equilibrium constant and state a conclusion about the position of the equilibrium. Remember that when we're solving for an equilibrium constant, we must always show just the expression to get full marks, and the expression is products over reactants raised to the power of their coefficient. The only thing that you can plug into an equilibrium constant expression are the equilibrium concentrations, and that's why we've already went ahead and solved them. The equilibrium concentration of PCl3 is 0.0540, and that's the same for chlorine. You can write this as 0.0540 times 0.0540, or if you want, you can write it as 0.0540 squared. I'm omitting my units here on the concentration since we don't include units for the equilibrium expression. And that gives us an answer of 0.044. That's the equilibrium constant value. Now we can make a statement about the position of the equilibrium. And remember, to make a statement about the position of the equilibrium, we always compare our K value against the number 1. In this case, since K comes out to be less than 1 as 0.044, the reactants are favored. If the answer came out to be greater than 1, we would say that the products are favored. In example number 5, we have a 1 liter vessel where 0.200 moles of nitrogen and 0.200 moles of oxygen are allowed to react at 773 Kelvin to produce nitrogen monoxide gas. There's nothing in that sentence that would indicate that 0.200 moles of nitrogen and oxygen are at equilibrium, so this tells me that I need an ice table. I also need to go off to the side and calculate the concentration that I'm going to plug into that ice table. So I've calculated the initial concentrations of nitrogen and oxygen off to the side. Since they both have the same number of moles, I could calculate that all in one step and plug that into my ice table. For the initial concentration, we're talking about as soon as the timer would be started, and therefore not enough time has elapsed to create any product, so that's going to be 0. Since we are making product, I will lose the reactants, and I will gain the product. Again, notice in this case that our product is twice as big as either one of our reactants, so we're going to represent that as plus 2x. Then our equilibrium line is the first two put together. So 0.200 subtract x, 0.200 subtract x, and then 2x. Once you get your ice table set up, you go back to the question for the extra piece of information. And in this case, our extra piece of information is that the percent reaction was found to be 12.5%. This means that 12.5% of the initial concentration has been converted over to the equilibrium. This opens ourselves up to a formula that we can remember. So when you're given the percent reaction, the percent reaction tells us that that is the percent of the initial concentration that has been converted over. Therefore, we can take the percent as a decimal, multiply it by our initial concentration, and that will give us the value that we've put into the change line. But notice that I've said that this equals to the positive change, because the subtraction sign in front of the nitrogen here and the oxygen indicates the fact that we are losing it. But when we multiply the percent reaction by the initial concentration, we want it to only equal the positive version of our variable. Therefore, we can take the percent as a decimal, 0.125, multiply that by our initial concentration, 0.200, and that will equal x since it's x in both of our change lines. When we multiply this together, we get x is equal to 0.0250. Now we have a value of x, and everything else after stays the same as example 3 and 4. In this question, we've been asked to calculate the equilibrium concentrations, so I can now do that since I know what x is. N2 at equilibrium is 0.200 subtract our x, and that gives us 0.175. And remember that we're solving for concentration, so we need to remember to add our units of either moles per liter or molar. The equilibrium concentration of oxygen is the same as that of nitrogen, seeing as we started off with the same initial concentration. That might not always be the case. The equilibrium concentration of nitrogen monoxide was 2 times x. So that gives us an equilibrium concentration of 0.0500 molar. Our last example says that the second step in the water-gas reaction involves reacting carbon monoxide with water vapor to make hydrogen gas. When 0.570 moles of carbon monoxide and 0.570 moles of water vapor are introduced in a 1 liter container at 600 Kelvin, they react to form carbon dioxide gas and hydrogen gas. Nothing in this question indicates that these moles are already at equilibrium. Again, I've calculated the initial concentrations off to the side to ensure that I can get full marks, and I've placed those initial concentrations into my ice table. Initially, not enough time has elapsed to create any product, so that's going to be represented by 0. I always lose reactants, and I gain products, and in this case, the coefficients are 1, 1, 1, and 1, so I'll have x, 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 and x. And the equilibrium line are the first two put together. Once you have your ice table set up, you go back to the question for the extra piece of information. And here we were told that the percent reaction of carbon monoxide was found to be 82.8%. Recall from the last example that when given the percent reaction, we have a formula that we can use to solve for x. The percent reaction times the initial concentration is always what's in our change line and the positive version of that. We were told that for carbon monoxide, 82.8% reacts. That can be represented as 0.828. The initial concentration is 0.570, and that equals what's in the change line for carbon monoxide. For carbon monoxide in the change line, the positive version is x. That might not always be the case, so make sure you always check your change line. Don't fall into the trap that it's always equal to x, because that won't be the case. Sometimes it might be 2x, 3x, or so on. Multiplying these two numbers together, we get 0.472 equals x. Once we know the value of x, we can now plug x into each one of our equilibrium concentrations to get the equilibrium concentration. So taking the value of x and plugging it into each one of the equilibrium lines will now give us the equilibrium concentrations of all of the species in this equilibrium. And we're going to use these concentrations in order to calculate the equilibrium constant. Before we can calculate the equilibrium constant, we must first write the equilibrium expression. Recall that the equilibrium expression is equal to the products over the reactants raised to the power of their coefficients. Here the coefficients are all 1. Plugging in the equilibrium concentrations that you've calculated into your equilibrium expression will set up a ratio as such. You then plug that in on your calculator, and when you do so, to the appropriate number of significant figures, you'll get an answer of 23.1. I strongly encourage that you take these numbers and plug them into your calculator to ensure that you can get an answer of 23.1. Make sure that you know how to use your calculator before the next assessment. The last thing we need to do to finish off this question is to state a conclusion about the position of the equilibrium. In this case, we have a value of k being greater than 1. This means that the products are favored. You've now been introduced to the two different types of ice table questions in the equilibrium unit. I strongly encourage that you practice the questions that follow.